Welcome back, students. Today we'll discuss about how we'll get equilibrium constant from Nernst equation and what is the relationship between electrochemical cell and its Gibbs free energy and how it is calculated. The first thing is that when you use a cell, then it gives voltage for a certain period of time. After some time, the voltage obtained from that cell becomes zero and we say that this cell has been discharged. So discharged, it means the equilibrium condition of the chemical reaction in the electrochemical cell has been achieved. Now see, to calculate the equilibrium constant, we'll see the general Nernst equation for the reaction of this type. You are quite aware about this type of equation in your chapter equilibrium. Now the Nernst equation for this reaction is E cell is equal to E naught cell minus RT by NF ln the right hand side expressions divided by, you will see the reactant side, the concentration of the reactants, the concentration of the products in the numerator, and the coefficients of this reaction has been written as the power. So E cell is equal to E naught cell minus RT by NF ln Q. Q means reaction quotient when the equilibrium has not been achieved. But when this equilibrium will be achieved, then the voltage obtained from the cell will become zero. So E cell will become zero when this Q will become Kc or equilibrium constant. So this expression is E cell is equal to E naught cell minus 0.059 by N log Kc. Instead of writing RTNF, we have put the values and temperature as 298 Kelvin and got this value of 0.059. At equilibrium, the E cell becomes 0. So the expression is only this right hand side will be there. E naught cell is equal to 0.059 by N log Kc, or log Kc is equal to N E naught cell by 0.059, or if you want to find the value of Kc, then you have to take the antilog of N E naught cell by 0.059. Now we'll solve one example 3.2 of your NCERT book. The question is given, this is the balanced redox reaction that occurs in the electrochemical cell. The question is, calculate the equilibrium constant if E naught cell is equal to 0.46 volt. Now this is the expression for finding the equilibrium constant. So here you need only two things. How many electrons are transferred from anode to cathode and what is the value of E naught cell. In the question it is given E naught cell, and if you will observe the equation, you will find that from anode to cathode the number of electrons transferred is equal to 2. So while solving the question, we will write first the formula. E naught cell is equal to 0.059 by N log Kc. Then in the next step we will put the values. N value as 2 and E naught cell value in the question it is given as 0.46. After putting the values and then solving it, we will find the equilibrium constant equal to 3.92 into 10 to the power 15. Next, we will know about the relationship between the cell potential and the Gibbs free energy. Now, Gibbs free energy is called as the electrical work done and it is equal to the electrical potential multiplied by the total charge passed through the electrochemical cell. So Gibbs energy is equal to this N into F. It is the total charge and this is the electrode potential of the cell potential of the electrochemical cell. So delta Rg is equal to minus NF E naught cell, or if we will calculate the standard Gibbs free energy, then instead of the cell potential, standard cell potential will be put. Now when we are using a particular cell, we are getting some energy. So that energy is being used in some useful work. So that is the free energy, and you know that free energy is having a minus sign when the spontaneous reaction occurs, and in electrochemical cells we get voltage spontaneously. So you will observe that a minus sign is there. Next, let us know about the relationship between the Gibbs free energy and equilibrium constant. So Gibbs free energy under standard conditions. So we know this is the expression for getting the equilibrium constant from the E naught cell. E naught cell is equal to 2.303 RT by NF log Kc, and this one is the expression which shows the relationship between the standard free energy change and the standard cell potential. Now in place of E naught cell, if we will put these values, then we'll get the relationship between the standard Gibbs free energy change and equilibrium constant. So by putting the value of E naught cell, that is the expression of equation 1 in equation 2, and solving it, the relationship is delta G naught is equal to minus 2.303 RT log Kc. Let us solve one example, one question, exercise 3.6 of NCERT book. In the button cells widely used in watches and other devices, the following reaction takes place. Determine the standard Gibbs free energy change and the standard cell potential for the reaction. Now how will we solve it? We know that the standard cell potential is equal to the standard electrode potential of cathode minus the standard electrode potential of anode. Now here first thing you have to identify anode and cathode. We will see that zinc from zero oxidation state, it is changing to Zn2+. So it is the anode, and silver oxide, you will find the oxidation state of silver is +1, which is changing to 0. So silver is the cathode. Now the values of the silver electrode potential and zinc electrode potential will obtain from the electrochemical series, and after referring that series we have found the values and put here in the formula, and E naught cell value is equal to 1.56 volt. Next step is to find out the standard free energy change. So we will write the formula delta Rg naught is equal to minus NF E naught cell, and here we will put the value of N. As you can see from the balanced equation, the number of electron is 2. Faraday constant value is 96500, and E naught cell we have already calculated. We will put it and solve it. Then this is the value of the standard free energy change, and you will observe that a minus sign is there. Students, I think this video will be quite helpful for you to understand the relationship between the standard cell potential, Gibbs free energy and equilibrium constant. So thank you.